My name is Matt Sherrier.
I'm Ashley LeBlanc.
And we will be giving the final presentation for the solar stack. Now today, I'm going to be walking through you guys the problem definition, the design requirements, a brief system overview of our 4 subsystems, the test results, as well as some of the lessons learned, and then I will be willing to answer some questions. So, we have shown this graph before, or this diagram before. This is the cycle overview that we were working with. The orange square indicates that our project was specifically oriented with the first step in the cycle. This is the part where concentrated solar energy comes in and is converted into the chemical bonds. Now, a few important things to note from this. If this cycle is run perfectly efficient, you do not run out of cobalt dioxide, which is a huge advantage of this process. And it is also an excellent way to store solar energy, which is one of the issues with solar energy. Now, onto our problem definition. We need to design our system within the constraints of the cycle. This means using the particles specified in the cycle in the slide before. We couldn't use some other inert particles such as sand or things we tested with, such as talcum powder. And we needed to operate within the facility that is outside. This constrains the amount of solar energy and temperatures we could get up to, as well as the spatial dimensions we had to use. Our mechanical design requirements, we needed to have a mass flow rate at least 0.5 grams per second. We also needed to cool the particles at least 500 degrees C per second, as well as collect 90% of it. Additionally, we needed to tumble the particles in a consistent cloud, as well as meet some dimensions and durability specifications. Onto the electrical design requirements, we needed to have at most 3 cables running between our enclosure and the user. We also needed to output the readings of the thermocouples that are at least plus minus 10 degrees C in accuracy, as well as store that data. We needed to specify the locations, have a hazard alert system, as well as efficiently deliver particles.
I will now talk to you about our mechanical system, each of the subsystems and how they came together, as well as addressing some of the issues we ran into and how future iterations could improve upon them. So our first subsystem is our power delivery system. We ended up designing a auger hopper system to deliver a known controllable mass flow rate. You can see the final CAD drawing up in the top right or left corner. So for this design, we have a hopper where you can put the powder into. It holds up to 2,000 grams, so it can fit plenty. And then attached to that, we have a chute, and within that chute is a nylon 3D printed screw. And on the back of that is a gear, and that gear meshes with another gear that's driven by a stepper motor. And as the stepper motor runs, it turns the screw, which each full rotation, we deliver 1.13 grams of powder. And so, knowing how many times we rotate the screw, we now have a known and controllable mass flow rate, and that can be changed with the electrical system. And once the powder exits the screw, it falls down that chute and slides into the back of the reactor. And as you can see in the very bottom of the screen is our calibration curve when we tested this system to know how much we get from each full rotation. Finally, we added a lid and stir to put on top of that to ensure that the powder is stirred up and not come to the sides of the hopper. So some challenges. We found that because the cobalt is so sticky, we had some backing up in the chute. So once it left the screw, it would fall and slide down the chute. But it would start to build up upon itself, and sometimes it would reach a critical mass where it would then slide into the reactor. Other times it would just build up and start falling out the sides, which is of course undesirable. So to fix this problem, we are experimenting with changing the slope to make sure that we have the slope of the slide enough, it has enough momentum to fall into the reactor. Additionally, we've had some issues with meshing the gears. To fix this problem, we implemented a mechanical stop behind the gear on this screw so that it won't slide out the back, so that they are aligned with each other perfectly because the stepper motor is bolted down, and so now we fixed that problem. So for our cloud generation system, we have implemented 2 high temperature bushings to replace the 2 bearings from the previous iteration. The last one had a bearing up flush against the cavity, which didn't work very well because you had conduction both off the back of the reactor as well as off this shaft, so it got really hot and burned up. So we moved that back and put the sprocket in front of that to serve as a heat sink to dissipate some of that heat. Additionally, we added a chain tensioner so that the chain is taut the entire time and that the cavity is able to rotate both forward and backwards. Additionally, we've added a pulsating option, so we're able to quickly accelerate and decelerate the motor, as well as to jerk it around to help free up some of the particles that are stuck around the cavity, generate that cloud that we want. Finally, we've tested and worked with different non-stick coatings on the walls of the cavity, which will hopefully help us when we reach high temperatures and not have that stick. Though we have not run on sun yet, which we plan to do next week, so that will then be tested if that actually works. So some of the challenges with this cloud generation is that non-stick coating. We've experimented with a whole bunch. We've had some issues both actually applying it, getting the right adhesion. It would just kind of flake off. So we had to experiment with different heating it after we applied it, heating it before we applied it, as well as it doesn't function great not heated up. So we're hoping to get the function that it says when it's up at like 1000 C. Additionally, some of the cobalt still clumps in the cavity. That is a problem that we faced throughout the entire year, which has been difficult to really fix. We've had some options that helps fix it, but not entirely. So in future iterations, they could maybe experiment with adding, say, some kind of vibration to the cavity itself to help loosen the powder, or some other future options. Additionally, the bushings were not press fit like the bearings, so they did not hold the cavity in place, which was an issue for us. It would slowly slide out the front because it's on a bit of a tilt. So we thought maybe the chain tensioner would hold it taut in place, but that didn't work. We thought maybe we'd have to cut a groove out of the shaft, put a snap ring on to hold it on. That would be a lot of work to manufacture now. So finally we decided to go with a shaft collar, which will be able to just screw on behind one of the bearings, and that should hold it in place and solve that problem. Finally, the third system for the mechanical side is the powder collection system. You see a picture there. It's composed of a removable filter that is able to collect the particles that exit the reactor. And this is a very modular design that can be unscrewed, filter can be taken out, particles dumped out, and then replaced, so that the experiment then can continue. Additionally, we have a blower that offers suction as well as cooling. We have a T-shaped valve, or T-shaped component that the particles fall into the middle. From the left side, we're pulling ambient air that cools the particles, and on the right side is where the filter is then collecting them, and that offers cooling as well as suction to pull it out of the reactor. And then we have a butterfly valve on that left side that can be adjusted so that you can either get full cooling when you're having it wide open, or you can close it and then have this maximum suction coming from the reactor. So some of the challenges we faced with this powder collection was sizing the blower. There's a lot of components we had to look into. We had to figure out what kind of piping diameter do we want to attach this to, what kind of cubic feet per minute do we need for this blower to get the adequate cooling rates, what kind of static pressure do we need. So there's a lot of thought and calculations. We bought one that didn't work, so we had to return that and go with a different one. So there was a lot of process in that. Additionally, sizing and selecting an adequate filter was tough because we needed a really fine filter to capture all the particles so they don't get sucked through. However, the finer the filter, the less airflow you're going to get, so then you're losing suction from your blower. So it's kind of that Goldilocks effect you find like right up now. So that is the overview of the mechanical systems.
And I'm going to talk to you about our control system. Here we have a flowchart of kind of our whole system. In the middle you can see the compact radio. That's our most important part of the system. It talks over Ethernet to our LabVIEW GUI, and then we have some motors that it's controlling, and the thermocouple data that's being sent back to it. And then another part is that the steering motor up here is being controlled directly through the power supply through a 24 volt to 12 volt converter. And so that part is always running, but the rest of it is controlled through the compact radio. And then this is our electrical hardware. You can see a picture of our enclosure. At the bottom here we have our compact radio. On the side you can see our thermocouple panel, and then at the top there are some motor drivers and our power supply. This is an overall picture of our graphical user interface. There's some graphs for our thermocouples. We also have some control for our motors and our hazard detection system, which I'll go over each of these more in detail. And then we have our cavity rotation as one of our parts. We use the NI 9263, which is an analog output card on the Cerio. This talks to the advanced motion controller using a -10 to +10 analog output. This allows us to run the motor both forward and backwards. As you can see on our graphical user interface, the user can use the slide bar to indicate what direction and what speed, and then they can also turn the motor either on or off. Then for our particle feeder, we're using the NI9402 digital output card. This sends a 3.3 volt DC signal to our stepper motor, and the user can specify the feed rate, and then they can also select what unit they want. They can select grams per second, grams per minute, grams per hour, and kilograms per second. Here's an overview of our thermocouples. There's two different charts that the user can see. One of them shows the past 2 seconds of data so that they can kind of see what the most recent history is, and then the other chart shows 1,024 seconds of data. And you can see a picture of our side panel that you plug in the thermocouples to. Right now it's only hooked up for 16, but if we add another card on the Cerio, the user could use up to 36 thermocouples. And then this is a picture of our hazard detection system. On the right, you can see the current temperature being displayed for the user so that you can get an exact temperature rather than just kind of eyeballing it on the graph. And then the user can also show a location for each of the thermocouples, and then they can select a max temperature. So say the bearing needs to be under 300 degrees. If the current temperature would go over 300 degrees, which you set as the max temperature, the hazard detection light will turn red. And some challenges we faced with our control system, initially we had some issues with setting up our Cerio. The computer had a different driver than the Cerio did, so we had some issues with talking to the Cerio with our program. We also had some issues in the beginning setting up our example programs. Most of the example programs were set up for a specific chassis of the Cerio, so there were a lot of hidden settings that we had to try to figure out how to change in order to get those to work with our Cerio. And then we also had some issues with exporting our thermocouple data to Excel. We would input a certain file path, and we thought that if we went to that file path on our computer that we'd be able to find the data, but none of the Excel documents were updating, so we actually found out that the Cerio created the same file path on itself, so we had to try to figure out how to access that data, but now we were able to do that.
Perfect. So I'm going to walk through a little bit of our testing and results, the first of which is going to be with the mechanical system. So the first system requirement we had with the mechanical system was the ability to input a mass flow rate that was at least 0.5 grams per second. As you can see, we successfully used the screw feeder system, which ended up being a very linear and consistent mechanism to deliver our particles, which allows the user to deliver particles anywhere between 0.5 grams per second to 3 grams per second. Now, in Ashley's slide, you saw in the GUI that you can determine what units, so we also have the different options of units if you prefer kilograms per second or grams per minute, grams per hour. There's lots of different options that we have that you can use. Next up, we have the system requirement to cool the particles at 500 degrees C per second. Now, unfortunately, we have not been able to perform a trial run on Sun since the initial trial we did back in October, so that is still pending. However, we are planning to run a trial run on Sun this Tuesday, pending the weather, and if we are able to do that, then we'll be able to verify that component of the system. We have performed a lot of analysis on the airflow of our collection system, and all of the math tells us that we will be able to cool our particles that quickly. However, we won't know for sure until we actually conduct our trial run on Sun this Tuesday. Additionally, another one of our system design requirements was that we are able to collect 90% of the particles. In the trial runs we've done, we were successful in collecting 95% of the particles within the entire system, not necessarily in the filter. However, we weren't testing to see if all those particles would collect specifically in the filter. We were simply testing to see whether or not the system works in general. So on further iterations and further tests, we expect when we run the system for a long enough time that it will successfully collect a higher percentage in the actual filter. However, all of the particles will be in the system, so the users will still be able to recover a significant amount of the particles. The next system requirement that we addressed was being able to create a cloud in a cavity. During our tests, we showed a light through the cavity, and we saw that there was 40% light attenuation through the cavity, which means there was indeed a cloud. We could also just look empirically and see that there is indeed a cloud when we ran and spun the cavity, so we successfully met that design requirement. Finally, we had some dimensional requirements that we had to meet. Our reactor weighed 110 pounds, which was under our 150 pound specification, and we still have the test pending though for the durability, because we had one of our requirements be that the reactor system run for 50 hours on sun. We obviously are not able to conduct that during the winter. However, during the summer, the system will be tested during that time period, and we expect it to meet that requirement and be durable for both 50 hours in total over the summer as well as 4 hours constantly on sun. Now on to some of the design requirements for the electrical system. We successfully met our cable management requirement. We have a total of 2 cables between the terminal that the users can control the experiment from and the enclosure, one for power and the other one being Ethernet. Next, our thermocouples, after some experiments with an RTD probe, ended up being within 3 degrees accurate of the actual temperature, which is awesome. Now granted, the temperatures measured were at the highest about boiling water temperature, so about 100 degrees C, but we expect this accuracy to continue once the temperatures ramp up to the 500 to 1,000 degrees C range when the experiment's actually conducted. Additionally, we successfully stored all of the data in Excel. We created a functionality where it automatically backs it up, so there's no dependency on the user actually remembering to store the data. The GUI will be stored automatically, which is really convenient, so we met that design requirement. Additionally, the hazard alert system is actually described to work as we expected, and as mentioned before, the user can specify the units for the input for the mass flow rate, which was very linear and worked as expected. Finally, some lessons learned. We discovered as a team that working at very high temperatures with very fine particles is a difficult task, both in trying to model the behavior, but then actually, in practicality, performing experiments, especially when the powder used is extremely expensive, proved to be difficult. Additionally, we learned how to lead and work in a cross-functional manner as a team. This involved identifying which members of our team were stronger in certain respects. For example, Sam Copping worked for an entire summer on the reactor, so she had a lot of background knowledge that proved useful. Schaefer had experience welding, so we made sure to leverage his skills. Additionally, Ashley did a great job wiring and utilizing her resources at work to order our enclosures. So throughout the process, we really learned to identify each other's strengths and make sure to leverage that throughout the process. Finally, in general, a lesson that we will be sure to remember moving forward into our careers, that it takes a lot of iterations to create a successful design. Ways we could have maybe improved now that we know this lesson is perform more experiments concretely beforehand. However, moving forward, we've realized that it takes a lot of testing and a lot of failure to finally identify that design that will be successful. With that, a brief summary, I gave you the problem definition. We talked about the design requirements, the system overviews, our test results, as well as lessons learned. So with that, are there any questions?
So thinking about your cloud pumping challenge, and how long do you need a constant cloud for? Is it like 1 second, a couple minutes, or?
Yeah. So ideally, I believe it is a range, and the percentage of the amount of powder reduced goes up the longer it's on sun. But I believe it only takes about 30 seconds of it being in that heat to achieve that. And so while it helps while it is in the cloud, but even while it is clumped on the sides, it is still receiving that heat and allowing it to reduce. So
It's just a less accurate experiment, is that why?
for if it's
If it's clumped?
Yeah, well, so the clumping is more that it isn't as exposed fully to the sunlight because only part of it is exposed. But on the other side is if it's clumped on the side, it's not being collected. And the collection is where when it falls to the chute and then the air blows over it, that's when it cools. And in order to maintain your reduced powder, it needs to be cooled at a very fast rate. And so it would be great if we just leave it all in the reactor, knock it out, and then collect it. But then it would have taken so long to cool, it would have back reacted, and then you wouldn't have your end product. So that's really the main issue of the clumping.
Okay, so I like this vibration idea, and I was thinking about a washing machine, how
Right.
instead of going in one direction, it
Right.
changes direction. So do you think you guys could do that if you had another few months?
Yeah, and we are able to rotate one way and back the other way and jerk it around a little bit. We do find that it actually works very well at moving the powder around. That's one of the things we actually saw in the fall when we ran it for the first time. We were just messing around with things, and we decided, well, what happens if we kind of like jerk it or accelerate fast? And we saw power fell, which was awesome. And so now we can. Before we weren't able to go in reverse, we can do that now, and we can get really fast accelerations, decelerations. So essentially, yeah. But what we don't have right now is we don't have a program that automatically does that. That like after a second it jerks and then it doesn't. It's right now you just have to the user itself has to slide it around. So in a future iteration, you can make some algorithm that has like the optimal jerking and continuous motion.
You guys could do that, right?
Yeah, you're welcome.
Professor?
I don't know if you mentioned that already. I know you didn't constantly test the system for a long time, but how long can you run it for until the filter becomes full and then you have to stop, take the old filter, clean it out, and put a new one? Well, I don't know if you have done some testing or some measurements how long you can keep the system running before you need to change the filter.
Absolutely. So that is dependent on how much we're feeding in. So if we're having a high feed rate, we're using that 3 grams per second, we're pumping a bunch of it into the system, well then more power is going to come through the system and be collected, and then you're going to need to replace your filter much quicker. But if you're running it slower, because we don't have all that much powder, and so we anticipate being on the lower end of that 0.5 grams per second, then we anticipate being able to run much longer. So we don't actually have concrete numbers. That would be a fantastic experiment to run at different things. I imagine that's what they'll do over the summer to try to find that optimal max flow rate versus time run before we change filter and stuff like that.
So on that, I think Professor Olak was asking, so, you know, it's the feed rate and time, when you multiply those together, you get volume. So how much volume, you're limited by volume before you have to change the filter. So do you have just a ballpark idea of how much volume the filter could hold before it clog up?
Yeah. So it's a good question. We ran a lot of our tests using talking power and flour first, and one of the issues with them is they have, on average, they have a certain micron level per particle. They also have a lot of really, really fine powder that's below that well below the average. And so when we were running with them, that would get clumped. That would be the first thing that would go through and it sucked into the filter. And we find that you'd actually do suction pretty quickly because of that. However, we just the other day ran a test with the cobalt, which doesn't have those same properties. And we were able to, so we saw that the suction lasted for, we ran it for only 20 minutes, but the suction was still as good at the beginning as it was after 20 minutes. So we haven't had a longer test on that. I mean, physically, the filter itself can, if you just pour powder in it, could fit like 100 grams or maybe more. But I imagine if you just dump powder into it like that, then you're going to lose airflow. So that would be things you're testing to check.
And another point on that is that the filter is not up near the sunlight, so theoretically the user would be able to change it out during a run on sun if it cooled up too fast.
So I like how your lessons learned were very teamwork oriented. Do you give lesson learned for both mechanical and electrical engineering side of things? Like what engineering lesson did you learn?
Sure. I'll start with mechanical. And so definitely, at least for me personally, I don't do a lot of manufacturing. I don't do a lot of hands-on engineering. I've done all the classroom stuff, but I haven't really gotten a lot of chances to go out in the manufacturing lab and make stuff. And so I know for a while there when eventually we're gonna have to do it, and there was kind of that hesitation, and like it's out of my element, out of my comfort zone, and so maybe I pushed off. And I think some of the team members would agree. We pushed off doing that a little bit just because it wasn't something we were used to. But once we actually went in there and started just using the drill press and the bandsaw, I mean, they aren't necessarily all that hard. So once we actually started going out and making stuff, it was actually kind of fun. We were creating things, and it wasn't as hard or as scary or whatever as I had thought originally. So just the lesson I guess what we learned is it's embrace things that maybe you don't necessarily know, and the unknown is always a little more scary than the actual doing of it.
And I think for the electrical side, one of the big issues we ran into early on is that none of us had any experience working with compact Rio. So we figured it out as we went, but we had a lot of wasted time just fuddling through the file directory and really not knowing what we're doing. We didn't have a good context. So I think one of the biggest lessons learned, at least I've taken away, is I think we could have leveraged some of the documentation online better. And National Instruments is really, really helpful with providing resources. Even if you just call them, they can help you walk you through different things. So I think making a more concerted effort to build more of a context and an understanding of what the hardware is we're working with. I mean, you heard in Ashley's presentation, we didn't find out until the very end that the compact Rio saved the files on the compact Rio itself. We thought it was sending to the computer. And a lot of that was found out just through trial and error. So I think maybe working a little harder just to understand sort of the foundation of the hardware we've been using would have proven useful. That likely would have taken a lot more time. We still spent a lot of time just doing our best to work with what we had and what we knew. But in my opinion, that would be, I think, one thing we could.
Yeah, I agree with the point about being able to talk to NI about things, because I've noticed in my internship this semester as well that there's a lot of components that a customer either wants you to work with, or it's something that fits your job the best, and you don't necessarily know anything about it. So I found that calling and being able to ask detailed questions about it is really helpful. And we did do that once or twice with the CREO as well for our project.
Any other questions?
Thank you.